these data sets that had like height, weight, whether they were diabetic, like had all kinds of metadata with it, and he was able to predict like their age within 3 years and their sex and their like whether or not they were diabetic, all this stuff just from pictures of the back of their eye, and like people weren't believing them. And so then he would go to conferences and talk about it, and then he'd show them the images where it was analyzing what parts of the image it was paying attention to. He's like, and based on the vasculature, I can tell their age within whatever. And then the doctors were like, oh yeah, it's pretty well known that the veins get thinner over time or whatever. I don't remember exactly what it was, but like it gave people a lot more confidence in the model after he was able to explain what the model was paying attention to.
Yeah, I mean, that I don't know. He hasn't done that in the structured thing, but the image thing, he does that.
Yeah,
like the cat, you can.
How would you do that?
How is it actually easier? Like,
Well, so if you
how are
do a
gonna
fully
see-
connected CNN,
Yeah.
convolutional neural network, and you just go like back one layer, you can just colorize the image with like
Heat map, with the heat map.
yeah, like the
Heat map.
like one part of the
Okay,
image.
so it will
Which is
highlight-
activated, more activated and stuff.
Imagine.
Because that's where the most activation is. Then that's what is creating that class, meaning that the weights are higher for that area, and so
But
that's
when
how
you
it
were
shows.
using like these dense networks fully connected.
So what we, I think the answer was, or one that I think would work pretty well is on your validation, just when you're testing the accuracy of the model, introduce noise to one of the features, one at a time, and run it, and then see how much
that's really clever.
your accuracy decreases.
Yeah, so that's very similar to some of the things people do with images,
Yeah.
where they'll like take a gray box and put it in different spots of the image, run it through, and then see how their categorical accuracy drops or whatever. And then they could say, oh, well, when it was here, it couldn't do anything. But when it was here, it made no difference. And so then.
But again, that's only looking at each one as an independent, what you call a sensitivity. What you're doing is a sensitivity to each one of those variables. It goes through
enough data set, you're still not varying the other ones, but they vary naturally.
Okay, they're varying naturally. You okay?
Not just one. Input.
Okay. I now. So you're changing the whole data set, and then you're changing one item by a delta and seeing how that. Okay.
Yeah, and the noise is just
then
random.
Yeah.
Yeah, and the noise is going to be dependent on what the column type is.
Yeah.
Honestly.
Yeah, that's probably good. Yeah.
It's like words in Word2Vec, you can't just like randomly change words to other words. But you could maybe use synonyms or something. Or
NLP is going to be difficult because it's easier. How do you change a category? I mean, how do you change a category like that? Like as you're saying, NLP, even in the structured data.
Change it to something else.
How do you change a category? What is the delta for that? How do you apply
for
continuous
purpose,
variables?
You're right. You're saying change it to something that's wrong.
Something else in your.
And then you see if you're.
No, but
completely to a different word, but as a category that you already have. Random one.
Okay.
Yeah.
Randomly to a different category, you mean?
Yes.
Okay, because if you're just randomly changing it, you may change it in a space where there is no category. I mean, then you won't know what it is.
No.
So you have to change it to some other category.
That exists in your browser.
Okay. That may run into.
That's what your model was trained on.
Yeah. But which category? I mean, what is that? So you're saying randomly pick any other category rather than, because once you start picking one, then you're putting some bias in that.
I think he's just saying within the same category, just one of the different options within that category, right?
No. If you that.
So
just one that's not the correct one. Just
this
pick
is
one of the other
input.
possible, like.
Yes.
Yeah.
The other possible
But not from a complete
values.
Yeah, the other possible values.
In that specific embedding.
Yeah, in that specific embedding. Yeah.
In case you're using
embedding. Yeah.
And that's what. Otherwise, if you're not using embedding and they're whole separate features, it's much easier to go backwards.
Say that again?
Well, with embedding, it's harder to go back and see which one matters because it's an embedding. Otherwise, you should be able, if it's not an embedding, but it's a flat.
It's a continuous variable.
Feature gets its own variable, its own value.
Okay.
It doesn't matter.
Then you can just look at the weights. The weights that have the most or the least don't matter. But when it's an embedding, it goes through and the weights are on random positions of that vector.
I'm kind of seeing what you're saying. I don't know if I fully understand this still. So let's say your output is an image.
No, this is tabular. But.
Yeah, but now I'm going to work my way back to the tabular. But you're saying, well, we all know that it's sort of easy in the image case because every pixel is independent of every other pixel. And then you just look backwards one step in the network where you have something that is like higher resolution or whatever.
Last one?
So this is the next to the last layer, and then the final outcome is one of two, it's a dog or a cat.
Mm-hmm.
And so if it's a dog or a cat, then you just look back one layer and you get a pixelated image, and then you look at what pixels contributed to cat versus dog, and then you can tell where the cat or dog is.
But we want to go to the very original image.
So each time you go back all the way to the original pixels, then you've got mixtures of weights all the way through, and you'll never figure out like how much this particular pixel contributed to cat or dog unless you do what you were saying earlier, which was just change that pixel randomly, run it through lots of times, and see how that affects your cat versus dog.
In the image, there's so much data that no individual pixel is going to make.
Sure, that's the problem. No individual pixel. Each pixel may only be 1% of thing. You will never be able to figure out in any sensible way which pixel is going to.
With tabular data, it's not that much.
Yeah, so tabular data is much more information rich. Like there's a lot of redundancy in the image data.
Yeah.
So in the case of tabular data, you've got different categories and you have an embedding for each thing.
Yeah.
Right? So like maybe this is day and this is store and this is day since holiday. And each one of these goes through an embedding layer. And then there's, I think in the FastAI, there's just like 2 fully connected layers. And then there's a final output that is the sales.
Well, I think there is some, there'll be at least some non-linearity because you can't just have the fully connected layer.
Fully connected layer. It's like, usually batch norm.
Yeah.
And then
a ReLU or something.
Followed by a ReLU.
Yeah, there is a ReLU batch kind of thing. Yeah.
Yeah.
So
there's like
there is a dropout. There is a dropout. There is a ReLU.
And so
yeah.
To figure out which one of these, and there's dozens of them, which one of them is more important than others, you could just randomly select different values for them and move them through. Now what were you saying?
So if there was no embedding.
If there's no embedding.
And this was using, so for days, say, is one day, is Tuesday, and so each one has its own floating point, basically, which is 1 or 0.
Okay.
Then you can just look at, after training the models, you can see the weights between.
So
each one of those.
So these would have, let's say, 500. So there'd be like 500 weights here. And
yeah, you could just sum them up.
Yeah, so you could sum them up, but then you don't know which of these weights went to which of these weights. And So like, it may be the case that the sum of all those weights is really high, but it actually is unimportant because the ones that it was really high to down here were then later ignored because the weights further down the network were
So even without embedding, you still have a problem.
Yeah, no, it kind of is like kind of a black box after they get into the network because it could be the case that, you know, this one only has like one that is very high at all, but it's a really important neuron in this layer because it really strongly like informs the value of the sales. And all the rest of them are really low, and so the average weights maybe don't correlate at all to the.
No, average might not, but the sum, we thought maybe.
You could,
but as you said, later, it could have really high weights in the beginning, and then later disappears. It's completely disregarded.
There may be something you could do during training, paying attention to the gradients. Instead of just the final weights, but just over training, pay attention to your gradients, like for all the weights associated with this. And like, if they're just fluctuating all the time like crazy, then maybe it's not a thing that's really valuable. Like it never found that it mattered. Like it just let them fluctuate all the time and they never settled on value. Whereas things that like settle very strongly to a value, maybe are more important. I don't know.
Nice to have an output and then here are your features that actually matter.
Yeah.
Or in order. Because
So like PCA kind of gives you that. Like it's just like, you know, this describes your data with this percentage of the, you know, it describes this percentage.
But in deep learning, you don't have anything like that.
Yeah. I wonder if we could architect a system
That might be good.
to actually give that to you. In addition to whatever problem it's solving, it also gives you
At the same time,
importance.
there's another layer or something or another output.
Yeah. Assuming that you know, I don't know.
Some layer in the middle.
I mean, you can clearly do it with your sensitivity study. After you've trained the network,
Yes.
then run the sensitivity study, figure out which ones were important, and use that to train the more bigger network that also had the sensitivity as like, so the original problem is all I want to do is find sales. And so then you run your network, you train it all, and then you run the sensitivity. And now you have additionally, you know, this was a 0.4, and this one was a 0.6, and this was 0.0. You know, they each get a score of like how important they were. Then you run a new network where you are also trying to predict these values. But I don't know how to make those values, like those would be like on a per data point case. Like some data points maybe is the most important thing is the sales holidays. And other data points, the most important thing was what the store was. The running all your data through would give you the aggregate. On average, store was the most important thing. Or on average, you know, how many days it's holiday was more important.
Or could we do something? I'm trying to think is this, instead of doing the sensitivity, what if I take that out? Okay, I take a variable out and I train it, like the learning rate finder. Is my loss, I don't know if you can even train it.
It takes too long if you have a lot of
It took too long to figure that out. Am I training? No, all I'm doing is I'm going to watch an epoch.
Would this be similar to, see on the slides that Jeremy showed, where it's like, I forget exactly what they were, but it was essentially like what each layer of the network was like detecting.
Yeah.
Like where the early layers were like lines and edges.
Oh, yeah.
Progressively like deeper.
Yeah.
It's totally related to what we're talking about.
And then
Yeah.
Dee just brought up an article that
I remember reading a long time ago that created a model that could explain how we can arrive at decisions. So I don't know, this is the model, but here this thing is like, so they had asked like, I think it's supposed to predict the sport, and then it tells it why decided that this was baseball and two was the players who like that. So it kind of explains the important.
Yeah, this is pretty common in images. This is, I mean, even Jeremy shows that where he would show where the dog is and he would show where the light shining and all that, I mean, where the most activated stuff. But I don't know how, I mean, they do it in a tabular data.
It's hard to visualize because
They're not
they
related,
don't fit together like.
fit together like the pixels around and stuff to
So,
create that.
in neuroscience, which is where I come from before
Yeah.
computers, people put electrodes in the brain and then they just like listen for brain activity and then they show images. And then they talk about something called a receptive field for that neuron. And they can show that some neurons only pay attention to some parts of the visual field, like what's in front of you. And so that's like, it makes sense for if it's pixel data, that you can say, well, this neuron in our neural network only pays attention to like this area of the image.
Yeah.
And it's not actually paying attention to the whole image. But if you get sufficiently deep in these convolutional neural networks, it's the whole image. Like there's no part of the image that this neuron
Is not
capable of being activated on.
Yeah.
In the early layers, they only pay attention to just a little area of the image.
Yeah.
And so I think there's this problem of the deeper the network gets, the more difficult it is to say, why did this one thing trigger this one thing that happened? And without the convolution, you lose all aspect of that. Like the fully connected layers, you only have to go one layer deep before you just have no idea.
Really, they can only go that.
Well, because everything is connected to everything. So like there's no like receptive field like there is in a convolutional network. The receptive field for a convolutional network has to do with like how big the kernel is and what your stride is and stuff like that. Whereas in a fully connected, like I am capable of being activated by everybody in the previous layer.
I mean, these are not very deep layers. I mean, whatever structured data you're using, yeah, there's a lot of embeddings. But if you look at this, there is only 2 linear layers. Goes from in features to out features of 1,000 and 1,000 to 500. And then there is batch norm in between these things. There are batch norms in the 1,000 layer, and then there is a dropout here too in one of those layers. So.
Yeah, and that's what I was saying, that when they're fully connected layers, these linear layers,
yeah,
you only need one layer before you lose all interpretability.
Okay. Okay.
Like this neuron is paying attention to only store or only days of sensolity or whatever. Like it pays attention to everything.
Using Lime for structured.
I think there's something that you could do. Good to almost any. It's like this is a supervised problem because you know the answer that you're looking for. But then like coming up with these is after you already know the task that you want to do, the supervised task, this becomes unsupervised. You can just run through and generate the data. All this. You don't need someone to label, those. You can label that algorithm. Have you ever heard of something called synthetic gradients? So there's a talk or like a little video on YouTube by this guy. And one of the problems that people have when they want to train really big models is that they have to spread it over lots of GPUs. And one of the problems is that there's this like locking that happens because in order to calculate the gradients, you have to send a single sample all the way through the model in order to backpropagate the gradients. Mm-hmm. And so like you have to lock all of the steps so that like all those GPUs have to wait for the slowest of those GPUs to finish running their parts of the model through before you can backpropagate all of their gradients. And so in order to like get past that lock, what they did is they made a network which had like a little sidecar neural network that was predicting what the gradients were going to be. And then they just said, let's just go with the prediction. And then they backpropagate the real gradients to train the gradient predictor. They call this synthetic gradients. And they were like talking about how like much faster they could train these distributed networks with it, but also you could train recurrent neural networks with it, and it like lets you go backwards in time much further than you normally would be able to. I don't understand it exactly, but it seems really cool.
Yeah, because they say because they accept the synthetic gradient, but then they say eventually it'll get corrected because the synthetic, they're not waiting for that for the real gradient, but eventually you will catch up with that because the synthetic gradients are a result
it's like
of
an
the
eventually consistent
consistency. Yeah.
I don't know who was behind that either. Yeah. The YouTube guy was Aurelian or something. I don't know. Some of the people from Farrar were reading his machine learning book. Python, machine learning, something.
Yeah.
Yeah, this one, the Lime, if you guys, I mean, this is one of the things which tries to predict how it is arriving at that particular answer through the Lime thing. So here they're showing an example where in an NLP case, again, they're using this for a decision tree thing. They're saying, okay, which are the words that actually made it come with that thing. So I just don't know how much they've used the Lime and the local interpretable model agnostic explanations. Machine learning classifiers, but they're talking about classifiers here and support explaining individual predictions for text classifiers or classifiers that act on tables. NumPy is a numerical. So, okay. Yeah, I have not played around and I would not I don't know how to images with the, they do that in the images and stuff, how they do that with the Keras and how they're explaining and all that stuff. But it's something that I've heard a lot of people have used. I haven't looked at the many, gone into any YouTube videos or stuff to actually see how they use it within a deep learning model. Somebody, okay. You just posted something.
Oh yeah, just that synthetic gradients video.
Oh, okay. Oh, this, the synthetic gradient. Okay. Then we looked at, basically we had already looked at, basically it's just you do, once you've done this, you go through the same thing. Hey, I go through a learning rate finder and all that stuff. It's about, once you do the get the embeddings done, you just go through the same thing as hey, I'm concatenating the embeddings from all the categories, and then he's doing he does an embedding drop in between just after concatenating all the embeddings. He takes, because there are various category variables, he takes the embeddings and then he makes a big vector out of that.
Oh, okay.
And then torch.cat x comma 1, and then he also does a drop of, I don't know what an embedding drop would do there, because it's just a dropout layer. So it'll drop out some input, I suppose, some of the embedding values, I suppose, or the connections to the, yeah.
I've been thinking about.
And then he's using the
dropout a lot lately.
And then he does a batch norm of the continuous variables, and then he's concatenating the embedded variables with the batch norm continuous variables. And then he does, after that, he's going through linear self dropout, f.relu of L of x, basically linear of this relu of the linear layer of that x. And then he's doing, if you do a batch norm, then after the relu, he's doing a batch norm on that. Because then he's defined two different, I mean, because he goes through that self dot in zip of self dot linears, he's defined, what is it, size I plus 1 here, range len of sizes minus 1. So he's defined the, what do you call the sizes is defined elsewhere, how many counts. He says how much of that, and I mean the sizes is about, he's defined this list here, which is a 30,500 thing there, because he's already defined 1,000 and a 500, and then he's defined how many of the embedding plus the continuous variables I have. So he knows how much output is going to come out. So he knows like how many, because he's concatenating the embeddings plus the continuous variables, so he knows how much he's going to get out, and then he's saying then he's going to 1,000 layer and a 500 layer after that, using these batch norms and things. I mean, he's just going through a linear relu batch norm on top of it. Go to the next one, relu batch norm on top of it. Just I mean, as you said, two linear connected, the fully connected layers with relu's batch norms on top of it. And then finally, he's doing a dropout at the end too. You see here, he's doing a dropout here. Is this a dropout? Probably.
D. Who knows what it is?
Who knows what it is? D. Yeah, D is in drops. Drops. That's what he's defined drops as, is dropout.
Okay.
So there is an embedding drop. He defines a different dropout for the embedding drop because he wants to use different dropout ratios. Because the embedding drop has a different dropout ratio compared to this drop, which he defines because there is an embedding drop and then there is a drops here. Because he's defining two different drops for the 1,000 and the 500 layer. Different dropout probability. That's why he's having that. And then ultimately he's just going through an output of X, which is just a linear.
But he's doing dropout.
Linear layer.
The embedding too? So he has a dropout for each of the linear layers and a dropout?
He has a dropout of the embedding layer. After embedding, he's concatenating all the embeddings. And then he's having a dropout after they come out, and he's concatenating all the embeddings.
So you can treat this as all of one.
And then he has a dropout layer here. And then he comes to the continuous variables. He applies a batch norm, and then he's concatenating the category with the continuous variables, and then he goes into these batch relu, batch norm, relu, and then dropout, then batch norm, relu, dropout. And then he comes out with that one value at the end. So, well, he does a sigmoid on that. So he's not doing one value at the end. I suppose he has to predict something. It's a range.
Well,
I don't.
If it's multi, he does one thing, and if it's not, he does a different thing. So
yeah,
that's.
If it's multi, he does a sigmoid. Otherwise, he says, I'm just going to predict one thing, so I'm going to do softmax instead of that. So, I mean, he's written it in such a fashion. Again, you go through the normal stuff, and he also has to, because of Y range, whatever you're trying to predict the sales, that's what they're predicting. Sales has a huge range, so he has to have a range that he converts the output back to the range of what the Y should be.
Oh, okay.
Because he's giving the YL as a log Y, because what he's feeding is a log Y into it, so that he has something more similar data as everything else in that 0 to 1 kind of range, within that 1 to 2 or something like that. And then so it is 0 to 12, the range is, so it's
So
e to the power of 12.
Instead of doing that,
Yeah.
couldn't he just not put the sigmoid layer on the end and let the network predict the actual sales value instead of like the log of the sales value? I don't know, maybe there's numerical reason.
Numerical reasons he may go on that for training purposes, the sigmoid, and yeah. Yeah, there are various ways. I mean, but it's once you put that, I mean, most of the work is in the engineering of the data. And then the deep learning is okay, put a few layers here and you train it and you see how it turns out, and you can adjust a few dropouts and stuff. And this is what he says, use the number 3 who got in the Rosman. I mean, they used a similar technique. And uses an atom and all that. And so you do the same thing as the image data. You do a learning rate finder, you go through this, then you start learning that, and then you can put a ALR scheduler, learning rate scheduler on top of that. You can do a cosine annealing. So all that stuff, whatever works in the image thing works here too. Everything, all these techniques works out there. Then I remember he's saying something, we'll talk about it more later. He talks about in the deep learning 2 called, he's moved away from this kind of cosine annealing now in the deep learning 2, because there's something called superconvergence. This Leslie Smith has come out with a way called superconvergence, where it's more like you start off with a low, go to a high, I think, and then come down, and then. So he was doing this in deep learning 1 before he knew those techniques, but.
I think superconvergence is like a triangle.
No, but what happens is here at the end, it goes really slowly, or not so, yeah, really slowly. It goes like that. Yeah, so the slope changes at one point.
Oh, really?
Yeah.
Oh, okay.
So, yeah, it goes up, it comes down, but then at some point at a low enough thing, it does this. And
well, then there's also momentum.
Yeah, there's also momentum that goes the other way.
And it's doing like
this. Yeah.
And does it also do that?
I don't know. I haven't gone into that paper to look at that. Yeah, so they play with the momentum and the learning rate at the same time, because all we've been playing around with is just the learning rate, and we drew cosine annealing and stuff. And then this guy, Leslie Smith.
Yeah, I feel like it opens the gates of like hyperplane or hell. Because it's like, well, now we've added momentum, and then we also add,
No, but it's not a hyperparameter, but you're not trying to
there's a fit of hyperparameters, because it's like, well, how far does this
go? Does this go? Okay, yeah, right. Okay.
Where do we do this? And like,
I know.
But
ultimately, all this deep learning is about engineering. You try different things and stuff, and how do I make it do faster and I can do less epochs and train faster.
No, I'm just feeling
yeah.
We went from 2 hyperparameters, and now we've got 6.
Yeah. Since it's gone to. I mean, we have to find something. Maybe there is a momentum find. I don't know how he does that, but there is he uses a heuristic from this paper, what they've used. But this paper only came out in February of 2018. So that's why he didn't know this in the deep learning 1. Yeah. But then in all his deep learning 2, which he taught in April and May, he's now gone on to this. He said, I don't have to do all this cosine. I just do this and I get the answer.
So this Open Review Net is really cool. If you guys haven't seen it.
No, I haven't. Is this different from ARC's archive?
Yeah, so archive is where the actual papers are published.
Okay.
Open Review is for a handful of different conferences. ICLR is one of them.
Okay.
And they publish the reviews openly. So if you click on this, you'll get to see what the judges, the different reviewers said, and then the responses from the author. And like in this case, there's a little bit of a talk here about
acceptance decision, why they accepted this paper and stuff, or
they actually rejected this paper. The decision is reject, but then you
Really?
can see exactly why. Yeah.
where do you see reject?
2/3 of the way down.
Oh, really? Oh, yeah. Okay.
Yeah, but this open review thing is really cool. because
Okay.
You can take whatever your paper is that you're like interested in, and you can see like not just the paper, but also like what experts in the field are saying about that paper, which often case is like easier to understand than the paper itself.
Oh, boy, I didn't know that they went into this conference. They would go into that kind of detail, like because the reviewers were not convinced because the effect is only observed for one task. So they question the significance of the result and stuff.
Yeah.
Okay.
But
But,
then if you scroll down, you'll see every reviewer's like
okay.
like what the reviewer said, and then
Oh, I attempted to reproduce the work in TensorFlow. So they're actually going and doing this.
well, this is a separate thing for this.
Oh, this is somebody else. Huh?
This reproduction thing is another cool thing.
Oh,
So there's, I think it was only for this 1 year, this
Yeah.
ICLR 2018. They
yeah.
put out a sort of like a challenge. I
Mm.
think it's called the reproducibility challenge. You
Ah,
can pick
okay.
anything that was submitted
Yeah.
and try to reproduce it. And then I sort of like blog posts about like, here, I tried to reproduce it and it worked or it didn't work. And then the
Okay.
judges use that to additionally make decisions on papers.
Well, so they may accept it next time, maybe. I mean, based on the
Sure. No, I'm
reproduction.
not saying that-
Yeah, because the reproduction would not have been done by the time the reviewers saw it, because this paper would not have been out in the domain at that time, or when the reviewers are looking at it.
I don't know when ICLR 2018 happened. I think it was in January or something. Maybe it was in February.
Okay,
I don't know.
because it says some conference blind submission.
Yeah, so I think they have different categories of submissions. So like
Okay.
sometimes people are asked to submit
Okay.
based on their previous years of like expertise. So like,
Hmm.
you know, like Jeffrey Hinton and his people will be like, would you submit a paper for this conference? And then blind submissions are just like unsolicited. off the
Unsolicited,
street,
so,
and then
okay.
it goes through review.
And then general reply to the reviewers' comments, they've replied to that. So this is cool. So you're able to see a lot of that thing that you wouldn't have seen,
Yeah.
because they're trying to reply to why you rejected what we did, because based on the reviewers' comment, it's apparent that is unclear. Yeah, because he has used, that's why, he's taken it. Jeremy has taken it and said, I'm going to use this. And I'm
No,
getting
Jeremy
good
really
results.
likes this guy.
Yeah.
And he really believes in his results. And the community, and I think he even mentions it, like mostly people are ignoring this. And Jeremy is
yeah.
like, you guys shouldn't ignore this. This is like one of the reasons FastAI is
Yeah.
like winning all these speed competitions.
Speed competitions, yep.
Is because they're doing
That's
this and nobody else
is
is
doing that, because that's the other thing. I saw the Downbench speed competition. The CIFAR 10, the top three are them, basically. It's FastAI student, and then the FastAI team, basically. Top three are them. And then even in the ImageNet, I didn't see a lot of CIFAR 10, I didn't see a lot of companies competing on that, but the ImageNet, a lot of companies like Intel, Google, and all that stuff, but he's still like fourth or something on that stuff. And he says, but he's like pretty good on the cost too, on the thing. And he's saying, hey, I've trained it using, like Google they're using these TPUs, which are not even open to the public. You can't even tap into some of their TPUs that they've used. And he said, I just used a general P3 AWS instance, and I've been able to do all that stuff. And then he claims in the cost, I think they've put his cost as $75. He said, I used a Spot instance, which was only cost me $25. So I should be in the top of the leaderboard on the cost because I just picked
but everybody could use it.
spot instance.
Right?
Yeah, but no, because they're all using, they can't use a spot instance because Google is using their own proprietary things.
Well, no, but like everybody else who used a real P3.
P3, yeah.
And
Could have.
paid for the full
Oh, yeah.
instance cost.
Yeah.
Could have used the spot instance instead.
Oh, yeah.
Like maybe they would have had to write a little bit of code to recover in the case of
Yeah.
your spot being taken. But
Yeah.
and
This is
actually, I don't
the,
even know if they did that. Like maybe they just used spot instances and tried.
See, number
to
4.
just try again, like,
yeah, because his complaint was this is all winning Google. This TPU version 2, nobody can even use. I mean, it's not something I can tap into this.
yeah.
Is his thing. Hey, I can only use what I can. I mean, P3 and stuff, what is open to the public. They bet all this stuff, but I don't have any way of using this. And then he says, if I had used it, I can use some better better way of doing this and come on top of this.
Yeah.
So, but that's huge. I mean, they're using half a TPU V2 pod and stuff. But the problem is if they're using this, how do they, the same thing is not winning the cost though. If you see this ResNet 50, this model or half of a TPU V2 pod, this AMBA-D net, okay, they did win the thing. No. How do you assess the cost of this one, which is not even available to the public? How do you even assess that?
You don't. Yeah, I don't know how they do it. They must have some way to do it. Like
Yeah.
give it a cost.
Yeah.
How much energy it uses?
Yeah, no, I don't know.
Well, TPU 1 is available, right?
TPU V2 is not available.
The first one is though.
First one maybe it is. Yeah, the first one is available. I think that's what you can go to the Google Cloud.
I've never tried
TPU. Okay. Yeah. But V2 is not available. So unless they are saying that's what we would price it in the market, I don't know. Yeah.
It will be cheaper
Yeah.
than GPUs. One TPU is like 4 GPUs.
Oh, one TPU.
That's what they, by speed.
Oh,
They
okay.
compared it.
And then the cool thing about it is they give you all the code. Everybody puts the code that they actually trained it on. It's all public.
Oh, that's good.
So you can see how Google trained it on their TensorFlow and all that, ResNet, benchmark PY, and yeah, you can see the whole thing, what they did. Train a ResNet thing. And so but in the CIFAR 10, if you look at it, I mean, he beats everybody there so the 30 minutes. So he's there at 3 hours and stuff in the fast AI, which he claims, hey, I bet Intel, who's using like crazy amount of 128 nodes with the Xeon Platinum thing,
Well,
36 cores and,
That's not a GPU, right?
Okay,
It's just like a lot of
C5, yeah.
CPUs.
Why would they do that? I don't know.
I think they just wanted to like, that's Intel,
Yeah.
right? So then
Yeah.
they're not gonna make a GPU, so
Yeah.
they're like, you can do it.
I
mean, they're
actually using AMD.
Yeah, well, I mean, Intel and AMD are both investing heavily into like chips to do fast matrix multiplies for neural nets, right? Like to get things out on the edge and do inference on the edge.
Yeah. Oh, yeah.
I think it's coming. It's just going to be a couple of years.
On the CIFAR 10, they just won the number 1, number 2, number 3 is all because he says the BKG is a fast AI student, and these are teams with Jeremy and stuff. So they've trained the whole thing from scratch in like 3 minutes, the first one, and the 5 minutes,
On
6.
B100s,
Uh-huh.
B3X16 large, yeah, that's really beefy.
That's beefy.
Yeah.
Okay.
It's
probably P3 2X large, but he says it only took him to 26 cents to do that because he's only used it for 3 minutes.
3 minutes, yeah. Sure.
Yeah. So yeah.
Well, no, the cost is on
That's
Paperspace, so that's a
Paperspace.
different, yeah, that's different. So the cost.
Yeah, cost and
longer.
Paperspace is the lower one. So we don't know whether this one he may have submitted
I wish they would
this.
show the cost On the ones that won the.
Won the thing, yeah,
speed
they're
and
not
ones
because,
that
yeah, because these may be two different things. This guy, they may not have won the thing, but they may have won it on the cost, but they may not have won it on the time.
Yeah, it looks like $1.18 for the one that's
Yeah.
8X.
Yeah, this is the AWP3, yeah, that's what it costs, $1.18 on that. But this guy must have, this BKJ, he did it on P3X/2. But he got only 29 cents, so I don't know.
It took like, just twice as long, more than twice as long.
Yeah, more than twice long. But after the 35 minutes, you go, it's an hour.
Yeah.
It's like,
Well, and are they only showing the top 5, or do they only have 5 people?
no, all submissions. There's a lot more people.
Oh, okay.
There's just a lot more people there. Stanford
Okay.
people,
Okay.
because their own group is also doing that. Stanford Dawn source and stuff.
Looks like Google didn't do that.
Huh? Yeah, they didn't Google and yeah, Intel, you don't see them there.
Yeah.
So yeah, it's all the because Dawn Bench is organized by Stanford and they have their own student groups competing in that. I suppose they want to improve their thing, but it's interesting. All of these, I mean, he's used PyTorch.
Oh, some of them went way past 94%.
Yeah.
95.
Oh yeah, this is 94.82, and do you see a 95? Oh yeah, 95.29. Yeah, because the minimum thing is you got to get 94. You can stop as soon as you get 94.
All the sources there, that's kind of cool.
Yep,
Okay.
all the sources there to see how they did it. And this is a ResNet 164 is what these guys trained on, all that started at Stanford, but he trained on a wide ResNet, which is kind of different. Not the ResNet 34 and
It's
stuff.
not even an all-wide ResNet, it's a custom wide ResNet. So, yeah. Who knows?
Oh, custom wide, but the wide ResNet is a paper. I mean, so he has customized it in some fashion, I suppose, to make it faster. Yeah. So that's pretty cool.
All
Or
wire
just
ResNets are custom.
Just to do it custom.
Yeah. So yeah, that super convergence. I mean, I'm going to read that thing, read that paper, understand what exactly is the. I mean, how do they even come up with that? I mean, I can see it in his videos and stuff. He describes what it is. I just want to go through the thing and see what is their intuition behind. Okay, why do you go like this? I mean, he says, hey, when I have a low learning rate, I have to have a high momentum. When I have a high learning rate, I have to have a low momentum. So I suppose the momentum is about how much you add from the previous calculations, because you're doing an exponential weighted average. Or is the momentum different? Momentum is it a differential of the gradient?
The momentum is the exponentially weighted average. Of the
previous gradient. Yeah.
Yeah. And
so
as your learning rate gets high, if your momentum is also high, you can just have a divergent model.
Yeah.
Right.
Yeah.
And I can see that in my losses and accuracy plots.
Yeah.
They'll go down, and if your learning rate gets too high, it'll just shoot off.
Shoot off. Okay.
But if you at the same time lower your momentum while you're doing that, they don't totally shoot off.
So if you lower the momentum, then you're giving less importance to the current. I mean, you're giving
you're giving more importance to your current step.
Rather less importance to the previous steps.
Yeah.
Okay. That's why you can use a high learning rate based on that thing, but then you're okay.
And it might bounce around in different directions more with a really low momentum and really high learning rate. Yeah, and then he talks about, Jeremy talks about all these, even the conference papers and he keeps saying that one thing is, hey, a lot of conference papers, they have to put all these convoluted math just to get accepted, because the academic community requires a certain amount of math for a paper to get accepted. Otherwise, they will just reject it. That's the state of academics. And he talks about, because he shows an Adam paper. If you look at the Adam paper, the math is like, if you put it on Excel, you understand what's going on and what he is doing. But if you look at the actual Adam paper, it starts off with a whole bunch of math and all the signs and everything. You wouldn't know what is going on, what's happening. To the community, right? Yeah. It's like the people who were doing it before it was cool. And so
he says they don't refactor. That's another reason.
Yeah, the math.
Because this Adam method for this, which is the Kingma thing, I mean, if you look at that, she shows, you start off with all this stuff, the algorithm, and
So
it's like this math, okay?
So what's next on our?
Yeah,
Beyond
so
the Rossman. What was?
Rossman, the next one was the recommendation, the IMDb.
Okay.
We can talk about that.
Well, I don't know, like what people are interested in.
Interested because, I mean, this is lesson,
That and RNN stuff is like.
Yeah, the RNN stuff is the very cool stuff. The RNN, I mean, I didn't understand RNN until I went through his thing. I mean, how the weights and stuff. The RNN, I had a basic understanding of that, but how it shares the weights and all that stuff, I didn't understand until I went through his videos.
I'm still pretty fuzzy on it. I mean, I kind of understand how the weights are shared, but
I need to start doing that. I mean, one of the things Jeremy says is, just because you look at a notebook and you think you kind of understand, you don't understand until you've gone and done it yourself.
Yeah.
Okay, until you've, basically he says, look at the notebook, make a few notes, and then write it yourself. Because that's how you will know whether you actually understood the stuff or not. I mean, whatever questions you have, I mean, you print it out, you do either go through a PDB trace or you just start line by line and start printing out and see what is it actually doing. Because he says, you cannot engineer the stuff that he's doing. He says, whatever I'm doing, I'm sitting here middle of the night doing all the stuff, but you can't do that unless you understand all the things that are going on. You need to know, if I change this, what will happen here, what will happen there and stuff. So he says, you gotta know what is happening at each point. I mean, how is that shape changing? And how is the weight, what weights are applying? What is the shape of the weight vector and stuff like that. So that's his thing. I mean, yeah, I've only looked at his RNN stuff, but I haven't actually tried it, which I need to try. I mean, that's what I'm going to plan this weekend is start, because I've tried his recommendation, which is a simple deep learning model and the recommendation, all these stuff, because recommendation algorithms used to be done by the factorization, matrix factorization methodology. And I don't know, have you guys done any recommendation thing? You know what a matrix factorization algorithm is, or okay, because you have a bunch of users and a bunch of movies with reviews, and it's a sparse matrix. Basically, it's not because there are a lot of people. People have only seen a few movies. There's a whole bunch of movies. Few people have seen a few movies, but among the population, say if you take 1,000 people, one person may have seen 3 or 4, say 10 movies, but for the 1,000 people, but they've all seen different movies and stuff. So you have a very sparse matrix. And then you're trying to infer is, how do I know if as a user, if I like these movies, and some other users like these movies, and other people how do I now infer and say, recommend, hey, based on your, the way the movies you watched and way the other people have watched similar movies, what are the movies that you're likely to watch, basically. So you're trying to take a sparse matrix with a lot of null values, and then trying to build a very dense matrix, which will have values everywhere that you can go and say, this, I can now, I know you've given a rating of 3 for this movie and a 4 for this movie. You haven't given a rating of this, but I've taken all the data that everybody and stuff, I can figure out what kind of rating you may give for this movie. And then based on that, then I can start recommending stuff. Hey, based on what are the highest rating of what are the top 10 movies that you haven't seen that we can recommend, and that's how they recommend movies. Or you can do it in other, look at it in other ways is, what are the top 10 movies? Everybody has, I mean, what are the
top 10 movies advertisers have asked us to show you?
Yeah.
And that you might also
like.
more
than that. And it has been there for a long time, the optimization. And one of the things I remember is there was because Amazon started with this recommendation way back in even these 98, 99 and stuff. I mean, Netflix came later on, but they were using some kind of recommendation, this matrix factorization. I suppose they were given an award in 2013 or 14 for one of the, not for the Netflix prize, as one of the algorithms that had a very big economic the impact in the world kind of thing, the way that because that was a new technique they had or I can look up not the Netflix prize.
Well, the Netflix prize might reference that award, but
oh yeah, recommendation system. They may collaborative filtering. Okay, yeah, it all comes to the collaborative filtering. All that stuff is part of that thing. And then, I mean, Spark at that time, I mean, before the deep learning came, the way to do that was, okay, you can only do, okay, once you take a matrix and you're going to factorize and all that stuff, it occupies a lot of memory because you're building this whole set of huge, I mean, you talk about 1,000 films and 1,000 users. It's a huge matrix. You can't fit it in the thing. And then Spark ML came. Before that, the MapReduce, they used to do with MapReduce, and the Spark ML came, and they had a special thing on that to do this on a parallel basis. And let me.
Some of the guys, data science at work, talking to them, and like, how are you storing this matrix?
Oh, you don't.
And they're like, oh yeah, we can't store it. It's 1,000,000 by 1,000,000. What are you doing?
No. So
million, it's relationships between.
Yeah.
Well, it's got to be stored somewhere. I mean, maybe distributed, but like the data exists somewhere. So
yeah, but
lets them work on it in a distributed way.
Yes.
I don't know
but they want to execute it in real time.
Yeah.
Against that matrix.
Yeah. Yeah, you're not going to be able to do like sub-second latency inference.
No.
Anything.
Well, you can't like load them to RAM.
Yeah.
Even distribute it. Well, you could distribute it, but.
Yeah, how many network hops is it going to take to do it?
Yeah, I used to have
Then you, like, as soon as you introduce distributed, you have lots of problems. There's any reliability and partitioning and all kinds of stuff.
No, you're only training for the distributed thing. You don't, I mean, you're inferring, you're not doing a distributed, I mean, you can, but inferring is more easier. The training is what is difficult initially, the 1,000,000+, because, but you have to train every night or something. As new data comes in, you're not training all the time, but you do a nightly run of the training because you've got enough new data. Now there are more people who have watched this, and so you have to keep training. Training is what takes time because you need more weights. But the deep learning thing, what has happened, I mean, a lot of people have moved into the deep learning because you don't have to now have this whole huge matrix and all that stuff. You just train it in batches. You go through a batch, mini batch, and you use the deep learning techniques, and you're able to, without going through the MapReduce thing, you can train as good or even better using the deep learning techniques on the movie recommendations. And in fact, most of the people have moved to deep learning.
Yeah, you only need
just in that last 2 years.
You only need the full matrix for training.
Yeah.
And then once you're done training, you can distribute the data to as many nodes as you need to do as fast.
Fastest, yeah.
With embedding, you don't even need.
No, that's what you don't. I mean, deep learning has completely changed that thing. Before that, you have to do all that stuff before deep learning came because people didn't know how to train this thing.
So
it's
would it be safe to say that if you're looking at at machine learning positions and they're talking about Spark and Kafka and things like that, that they're a little bit old school?
That's a little bit of old school. Because if you look at, because I heard a talk by Facebook, they said, we've just moved to deep learning now. It's just because once the scale of stuff kept becoming bigger and bigger, now you have to throw, you can do parallel, but you have to throw many machines to do all this parallelly. The deep learning is what there is. I mean, I can find that paper. He said we've moved into deep learning models to do this much more efficiently. Yeah, they're kind of behind the curve on this because it takes people. I mean, they've
engineer your way out of it.
Yeah, you couldn't engineer. Yeah, and his deep learning thing. If you look at his Fast AI, Fast AI GitHub, we can bring up his thing. It's a pretty. They are kind of. I mean, it's the way to do it is through deep learning, because the way is because in deep learning you are not trying to. You just have tabular data. You never trying to put it together as a million row by million column like that. You're just using tabular data, and then you're going through and training it through epochs after epochs. Then you're getting your the similar thing. Whatever you're trying to do matter. You're just training it through multiple epochs to get there, learning rates and stuff. Yeah, it's like this guy. I mean, people are behind the curve. Like Deek was saying, like Charter, he's accepted a position in Charter, and they used the guy whoever left was doing neural net in a MATLAB.
There is a library for it.
Yeah,
Well, this is my team, so get over it.
But how much library are you going to, I mean, like the amount of NumPy libraries you can hit with Python and with even, I mean, Java is another thing, I would have believed if you had done it in Java. Huh?
I said MATLAB is surprisingly popular in the
scientific world, but yeah, you can do as a researcher, you can do, but not for production and stuff. I mean, if you're into production,
you gotta lay out the nose for a license too.
Yeah.
It's not free.
Yeah. Because I mean, MATLAB is the choice of use in scientific environments. Okay, I can represent things as, I mean, yeah, but that's in the past. I mean, that's what people are used to.
Yeah, no,
It'll take another generation for you to replace the researchers with the new one.
Replacement.
Huh?
From that.
Yeah. Yeah. I mean, NumPy, Pandas, and stuff.
Because it does pretty good plotting and stuff too.
Yeah.
But it's not a real language like Python.
No.
They bolted on language parts.
Yeah.
But it's not a real language. But what are people really interested in doing, like sort of for the next part of this?
Yeah.
Do we want to keep moving on to new content, or do we want to like go back and maybe enter a Kaggle competition or the old ones that have already expired, or do we want to like do sort of like a hackathon kind of meeting every few weeks where we don't just cover material, but we actually like have like for these 2 hours, we want to like actually get something working, going.
Yeah.
I don't know.
I wouldn't mind learning about the recurrent neural networks too, but then after that, we can.
I know that at least Matt Pitlick, who works at 1904 Labs, has expressed interest of like, well, if you guys ever do another Fast AI learning course, I'd love to get in, but I feel like you guys are already started, and so I would wait for the next one. But, but it seems like why not just like kind of go back to what the stuff we were doing and just do it in more depth and bring those people along. And
Keith Chester wants to enter a Kaggle competition or something.
yeah,
And he wants to do a presentation of his projects. So that might be good.
Yeah, he wanted to do kind of a hackathon night thing, I think he mentioned on there. And I had a data set that I thought would be really cool, this Dollar Street data set, where they've taken and hired photographers all around the world to go into people's homes of all income levels, all the way from like people who live in huts and then like people who live in mansions.
Yeah.
And they take pictures of like their house,
I saw that too.
and their bed and their sink and where they do dishes and their hands and their family and like, but it's like 250 of these like prescribed images.
Yeah.
And the metadata about them, like their income level and stuff like that. And so like, it's this really cool data set, whereas like, wouldn't you love to be able to look at one of these pictures and be like, can I use a neural network to guess what your income level is? And if I can, what did it look at in the picture to make that guess? did it pay attention to what you were wearing, or did it pay attention, like if it's your sink, like did it pay attention to this, like the shape of the sink? Like, I don't know, it's like, it seems like there might be enough data to actually learn a model to do the predictions of income. And then if there is, I think it could be really fun to post about it. And that it might be like something that is like a layperson would retweet or whatever. Like it seems like it kind of has that viral aspect to it. Neural network learns how to spot rich people or something like buy their shoes or something. I don't know what it will discover, but
I have a idea for an AI project, but I don't know if it's already out there. Like I've been always curious about, astronomy and whether aliens and all that stuff. So I was curious whether SETI, do they use machine learning to analyze?
I assume everybody in science, if they're not using it now, will be in the next couple of years. I listened to a talk, and it was by one of the guys who's in charge of the big supercomputing facilities in the United States. So there's a couple of these like big places where they do like climate models and like really big nuclear reaction models and stuff. And they set up the new supercomputer facility. So like every few years they rotate out like all of their racks and stuff. And he said that predominantly it used to be like C++ and like Fortran and like, and then like really beefy models with like beefy computers with like lots of CPUs and memory. He said now it's like everybody's asking for more GPUs and they just want like the basic Python stack of like Python notebooks and the Python libraries installed and like lots of GPUs. And he thinks that that's going to be the future of these big supercomputer facilities is going to be like, well, we can give you, 1,000 GPUs for an hour to do your climate models. So yeah, I don't know if everybody's doing it yet, but I think for a while it's going to be like the people who know how to do it are going to be like the alchemists who can write papers analyzing all the data, even if they're not super experts in it.
My idea for projects, there's probably a lot of data like stars out there. You can tell by the chemical signature from and all these just weird when the rotations and when it changes, if there's a planet there, and where there's life on the planet. So AI would be perfect for that because it can analyze all these billions of images of stars and look for the chemical signatures and stuff, and be a cool project to look for where there's life.
Yeah. No, I listen to the Science Friday on NPR too, and they always I used to love it more, but I don't know, maybe I grew out of it or something, but sometimes they got these citizen scientist call outs where they'll have an astronomer or people who collect moths or something will come up and be like, here's how you can get involved. And for the astronomer things, it's always we've put up a data set of 1 million images, and if you could go on and just label 2 of them, that would really help us out. And so I assume that what they want you to do is label their test data so that they can use machine learning models to actually do the real stuff. Whereas in the past they would have just been well, we're just gonna
show people.
Well, they're gonna have to show it to lots of people, and then the ones that match, then they can trust them. Yeah. But Andrew Ng sort of had the 1 second rule for what would be a good thing to apply machine learning to. It's anything a relatively intelligent human could do, just 1 second. If it only takes you 1 second to do it, we could probably do it in deep learning. That's a lot of things.
Yeah.
And a lot of things are just chains of 1 second decisions. If it's just a series of 1 second decisions where you don't have to have a long memory of what's going on, security guard or whatever, is that going? If you can figure that out in 1 second, which hopefully you can, because otherwise you can't have the reaction time to do anything.
Segway is releasing their drones, and Segway is control autonomously and recognize when people are fighting, and they send drones that can follow the bad guy. There's a whole video on YouTube. It looks really cool. And then on top of that, the security guard can jump on the Segway rope AI robot, and then the robot will take the side of it. It's actually YouTube video. It's really
Oh wow,
I'll show you.
that's crazy.
Let me send it. It's pretty.
I'm super interested if you guys are to like actually get our hands dirty during some of these meetups and dirty, like keyboard dirty, and like actually like code some stuff up. And Kaggle just released a new competition for taking the ImageNet data and then doing image segmentation on it. I think I didn't read all the details. I just got the email.
Image segmentation, the localization they had already done before. Yeah, Jeremy mentions about that in his deep learning videos, that you can get that data set and stuff and you can train that. Well, I didn't think it was a new competition. Because he had mentioned that on his videos.
Yeah, I don't see anything on their open object localization challenge. It's just for knowledge.
Yeah, that object localization, he mentions that, hey, you can get that data set and train that, and then you can.
What's the email? Oh, it's identify all objects in an image, not just the main one.
Okay. Okay.
It's the
which is again image segmentation. I mean, putting a class on every pixel and being able to identify the.
Yeah, this is a 12 years ago challenge, and it says now it's now.
Kaggle's 12 years old.
Well, that's what
No, but the challenge may not be, Kaggle may not be 12 years back.
Ago, 12 years ago.
Yeah.
I thought it was like, I did not know Kaggle has been around.
Yeah, maybe this is just a random, like you said you got it too.
I got something. I thought that's what it was,
but yeah, there's no money or anything for this.
No, there's no money.
I don't know why they sent out an email about it. There's only 16 teams so far. But maybe it's a new thing. But it is, it's not for money, it's just a knowledge one.
Yeah, so I mean, if you guys want to take a look at the collaborative, I mean, just so that, yeah, so we need to discuss how we're going to go forward. That's one thing. Hey, I mean, what do you want to do? I mean, the RNN is the next one after this collaborative filtering, it gets into RNNs.
Yeah.
I mean, that's what we can do is, I mean, it's a bear to start off. He starts with the language modeling. That's pretty character thing is what you want to go for, because language modeling is quite a bit involved. Because he starts with the language modeling, he gives you a result, and then he gets into the character by character, because he's trying to predict if my first 3 characters, what's my 4th character. But that's a good way to understand how RNNs work and stuff. He can say, hey, I can expand that to give this 6 characters, what's my 7th character and stuff like that. And then using that, he also introduces the concept of attention models and teacher forcing, which are really important in the RNN NLP space.
So this is data now. It's but Andre Karpathy talks about the unreasonable effectiveness of recurrent neural networks.
No, so yeah,
from 2015.
2015.
But that's sort of like what started my whole like.
Oh yeah,
with the whole thing.
Yeah.
He's talking about how you can take Shakespeare or Nietzsche or whatever and like build a bot that like spits out Shakespearean language or whatever.
Yeah. No, that also piqued my interest, but at least going through Jeremy's thing was, I understood how it's working. I mean, yeah, you can, and then the thing is, the problem he also comes across, a lot of online code is trash, is what he says. A lot of online code, people just put there, even the PyTorch language model, there is a sequence PyTorch sample code. The problem with that is they just don't even have a validation set. They just say, I'm going to do language translation model there. There is no validation set. He says, how do you even know if this thing has worked? if I don't have a validation set? They have not gone through the thing of, okay, here they're putting up, PyTorch is putting up a tutorial in there, and then they have not followed the principles of deep learning. Say, I need to have a training set and a validation set. And so he does the translation. He goes in the Deep Learning 2 course, he goes through in detail. But here, whatever he does in this first course is what Andrej Karpathy's thing is. It'll start spitting out poems on its own or literature on its own, like talking like Shakespeare or something like that. And then, or it was latex code, is you can, even if you put in the latex, it'll start producing latex-like code, latex-like thing. So, but before, I mean, that's just what he does to show off the power. Okay, you get the awe factor, but then you actually go into this character modeling to understand how exactly you can go back in time and how much time. And then there is also the memory issues, how far back you want to make it remember. Then you get into those LSTMs and how they introduce some hyperparameters in the GRU, which introduces certain hyperparameters. He talks about how those LSTMs work and stuff. I never understood that before. I mean, he talks about that and takes you. I still don't fully, because I haven't actually done it. I mean, it's like you see the video, you kind of understand it. Unless you actually go and do it, you won't understand it fully. And the LSTM is, the thing is, I mean, you don't have to build an LSTM, but it has these parameters. You have to understand what these parameters do. Because anything in PyTorch, you'll have to throw some parameters. It's like the momentum. Okay, I got to know what a 0.9 or a 0.1 means in that momentum and stuff. So, I mean, we can go through the RNN because that's the next deeper stuff, which is difficult to understand what is going on. And one of the things he does in Deep Learning 2 also, he introduces, I mean, you have to give it to Jay. I mean, he's doing a lot of new stuff. He says people are not just interested, they're just interested in churning out papers and stuff. And they're not interested, because he said he went to a lot of things, because he introduces a concept of the way we do transfer learning in images. He introduces how you can do transfer learning in NLP. He said he approached a lot of people in the NLP space, and how do you do it? And then they just said, well, you can't do that. And it's it's a waste of time doing this. NLP is different. It's not the same as images. But then he actually proves you can do transfer learning, and he trains it on a different set of data set and things. And then he says, well, I already have at least the model understands what a language is. Then he does something else with it, like the way we do with the image thing is, hey, the ImageNet is trained on all the classes and stuff, but what we have is certain our own classes, which are kind of different, but you don't have to do the whole training. So even with the NLP, he goes through the same thing he does on images. He trains one thing, and then he does the same thing as a transfer learning. He takes off the last layer, he puts in some other layer on that, based on what the thing is, and then he does a learning rate finder. He almost says, what he says is NLP is right now at a point like what images was in 2012. That there is just he says in the next 2 years, it's just going to explode on the NLP thing. Because people haven't done things, they haven't worked on this stuff enough. And like transfer learning is just getting into, as I do it now, there is a lot of interest. In the Twitter, there is a lot more people responding to Twitter thing on that transfer learning on NLP. So people are getting interested. He says, whatever that breakthrough, we're going to have a lot more breakthroughs on NLP in the next few years, like the way we had it in 2012, starting in 2012 on the images. So that's his take, and he goes through quite a bit on this NLP stuff, and says there is a lot of things that sequence to sequence learning, whatever he introduces the concept, he says, okay, he just says, I've shown it to you to do the translation from one language to the other. It doesn't need to be, I mean, it could be an image to text, text to image, any one of them. It's just, okay, you're taking an encoder and you're taking a decoder, and you can combine all the techniques because you're using the similar techniques that you use in images. You can now combine images with the with text, or text with images, or the other way around, and the translation and all that stuff. So that's something, I mean, we got to keep on top of that. It's again a new thing, but not a lot of people have done stuff. He says, hey, if you got a good idea, you probably can get a paper out of that because not a lot of work has been done in this area. So so the RNN is a good thing. Maybe it'll take us 2 weeks to discuss that and get a grip on what is happening in the RNN. I mean, it's easy to just see, okay, this block goes here and goes here, but how does it actually flow? How does the data flow? How is it able to remember? What is a memory means? Something we have to go through and at least understand in a little bit more depth of what an RNN means. So, I mean, that's one thing we can do. And
so would that put us at lesson 6?
That'll put us at the RNN. Lesson 6 is, as I said, lesson 6 is very involved language modeling. We would probably he goes off lesson 6, and then lesson 7 or something would be where he introduces the lighter version of the RNN, where he says, okay, now I'm going to tell you how to do it from scratch. Okay. Because in the language model, he does what Karpathy does. Okay, he's going to train it on a bunch of words. He does the word thing, and then he makes it spit out a paragraph. Yeah. And he says how a loss of 0.25 to 0.23 makes a huge difference. When a loss is at 0.25, it spits out garbage. Once he has gone a few more epochs and it's gone to 0.23, then suddenly you can make sense out of that. He says, because he says, okay, those kind of losses that you see in images, still we are very far from that kind of loss. We are still struggling at a much higher loss in NLP. So we have to still figure out ways to train it, figure out new ways that will work with NLP. Images, people have done a lot of work to figure out a lot of things. I mean, initially you have the VGG, but now he says VGG, nobody uses it. Just, yeah, it was one thing, but then it led to other things and stuff. So he says more and more new techniques are going to come into the NLP arena. Like even these guys, I don't think like Jane.ai, these guys are not using deep learning, because whenever were you there in that talk that they gave about 2-3 months back at the deep learning meetup, they were still talking about the old techniques,
so
which are.
I've heard them talk a couple of times, and Dave Costanaro says that they ensemble lots of different techniques.
Yeah, they say that.
And so like, yeah, I don't know.
No. But to get to NLP, the deep learning and stuff, you need a lot more skill set. Okay, you'll see that. You just can't, because the older machine learning techniques was, what is it called? There's a term for that, for texting. I usually have that on my.
Yeah, it might be a mistake if you were staffing up the AI or something like that to hire NLP people, because they're going to be like old school technique processing.
Yeah.
And what you really want is
the TF-IDF. That's the old model. TF-IDF, like if you want to, that's the old machine learning model. Yeah.
I think we got maybe in trouble last.
Oh, okay.
I don't know if it was because of what we were on the board or if we left trash.
No, we didn't leave any trash. I talked to her. She said, well, no, I was just telling you as a matter of fact to communications to all my groups.
Yeah, that's what she said, but I don't know. I always think that's just like
an excuse to be nice, could be.
So a couple of weeks ago, there was something already here.
Oh, okay.
And we added to it, and maybe we forgot to erase it.
Yeah, we didn't erase any of their stuff, but we did add to it. So maybe it was like.
That's maybe why it's to all the groups. Who knows?
Yeah. But I don't know if it was trash or if it was like just vulgar.
Yeah.
Before we leave, can we play that video? I sent it to you in Slack. It's kind of funny.
Oh, okay.
It's the other.
This one.
Yeah, it's the new segue.
Ah, okay. Yeah. Yeah, it's pretty.
Yeah, they resisted the urge to make us like that.
Here's where it gets fun. You're right, it's kind of slow, but I'm not outrun it.
Well, it doesn't have a handle, so it's like not that kind of.
Yeah, it's 11 miles per hour.
It's like.
Yeah.
What's the recording?
Maybe it's just the video.
Yeah, that was funny.
I just like it when he's up on the road.
But yeah, it's a
So,
little scary that we're like with off the shelf deep learning today. Like,
oh yeah, yeah. Deep
cobble
lens.
together something,
Yeah,
they like can do this.
yeah.
Like
Yeah.
what is going on at the government level?
Oh, yeah.
Where they're attaching guns to things and
Things and,
like
yeah.
nerve agents and whatever, and like that is scary world.
Yeah.
Well,
Yeah.
one day, like, mad at the Korean university, is they're running these autonomous soldiers at the border, and a bunch of scientists like stopped associating with that Korean university. They're ranked pretty high too.
I haven't heard about that.
Yeah, it was a couple months ago.
I know.
The
New York Times did a piece about Google engineers who refused to work
Yeah.
on.
Pentagon.
Oh yeah, Pentagon thing, they quit and stuff and,
Yeah, they
yeah.
said they weren't gonna bring in the contract. So
Hmm.
Google eventually caved, kind of. I mean, they're gonna
Mhm.
fulfill.
They
the
caved, but they
contract.
didn't. But
Yeah.
yeah.
I don't
But
know.
you don't think Russia and China and everybody's gonna use?
Oh, of course they are, yeah.
So they may not have as much restrictions.
Yeah.
I mean, from everything I've heard, China is kind of ahead of where a lot of like the bigger US companies are, because they have access to all
Data.
of that data that the government.
And their society is more,
Yeah.
they-
Uniform or,
Yeah, exactly. They're not gonna scream and protest about privacy.
well, they protest, but.
They I mean, they have those glasses, the police have the glasses,
No.
which can find people and everybody's on database.
No.
So you can find criminals easily. I can't do that here.
Yeah, I think I saw something about that recently.
Yeah.
that they have a bunch of closed circuit televisions that
They've already,
they spread around the city that have helped them find criminals.
at concerts, they've apprehended a couple of criminals now. Because they scam the audience, 50,000 people, and they find people that much. But they have all kinds of stuff. They have that social, you get a social ranking based on good deeds.
Yeah, that's
And then,
pretty dystopian too.